Hello students. So, in the last class we were solving some examples based on level surfaces and directional derivative. So, in the level surfaces we sort of try to cover a few examples where we can calculate the normal, tangent plane and things like that. So, I did try to show you one or two examples, and the rest of the problems can be solved in the similar fashion. So, you may try to look into some books which I have listed in the references and try to solve some examples. We will also try to include some problems in your assignment sheet so that you can be able to practice them. And we also solved a few examples on directional derivative. So, today I will solve one more example on directional derivative just to make the concept clear, and then we will move on to our next topic, which is basically the application of vector calculus in applied mathematics or in mechanics. So, that would also be an interesting thing to study in this context. All right. So, let us start with our very last example on the directional derivative chapter. So, find the directional derivative for the function phi x y z equals to x y z at the point 2 to 2 in the direction of I plus j plus k. All right. So, the solution. So, first of all, we know that when we are given a scalar function phi x y z or f x y z, so the very first thing that we do is to calculate the gradient of phi or gradient of f. So, the given function is phi x y z, then gradient of phi is del phi del x times I del phi del y times j and del phi del z times k. We are used to write f, so that is why sort of accidentally wrote f, but it is phi actually. Now, del phi del x is y z I, del phi del y is x z j, and del f del z is x y k. All right. So, then the gradient of phi at the point P, which is 2 to 2 equals to 4 I plus 4 j plus 4 k. So, I take 4 common, and then this will be I plus j plus k. All right. Now, the given direction vector, or I also prefer to call it as direction vector, because we have to calculate the directional derivative along the direction of this vector. Okay. So, the given vector A is equals to, what do we have? We have I plus j plus k. So, then our A cap would be vector A divided by mod of A, and then this will be I plus j plus k, and then square root of 1 square plus 1 square plus 1 square. So, ultimately 1 by square root of 3 I plus j plus k. All right. So, the required directional derivative. So, the required directional derivative, or we can write it as df at the point P, is equals to gradient of phi, sorry, not df, in this case it is d phi, excuse me. So, this is the gradient of phi at the point P dot product with A cap. So, what is my gradient of phi at the point P? It is 4 times I plus j plus k dot product with 1 by square root of 3 I plus j plus k, and now this will be 4 by square root of 3, and this will be I square. So, 1 square plus 1 square plus 1 square, basically the dot product, and then it will be 3. So, 4 times 3 divided by square root of 3. So, it is ultimately 4 square root of 3. So, that is the required directional derivative of the given scalar function phi in this case in the direction of the vector I plus j plus k, and we just followed the traditional how to say method to calculate the directional derivative, and this is how we obtain the directional derivative of the function phi. All right. So, I will stop with the examples on directional derivative, because I have tried to cover as many examples as possible. And now we move on to our next topic, which are basically an application or some applications, not an application, but some applications of vector calculus in mechanics, in a way, in elementary differential geometry and in mechanics. So, we will now learn the concepts of tangent, normal, binormal. There is a very nice formula called as Serret-Frenet formula that shows that how you connect in vector calculus the normal, the tangent, and the binormal of a curve at a certain point P. So, we will now move on to those topics, and today we will start with elementary differential geometry concepts, and then we move to those tangent, normal and binormal concepts. All right. So, basically, we will start with today with this tangent, normal, binormal, Serret-Frenet formula. All right. So, this is what we start with today. So, before we start with tangent, normal and binormal, we give some basic definitions and idea of what do we mean by a parametric representation of a curve, how do we define a curve in a space, and then we slowly move on to these topics. All right. So, let me go back to my notepad. Okay. So, now what do we mean by a curve in space? So, a curve in space. So, a curve, a formal definition goes like this. Basically, a curve is an aggregate of points whose coordinates are functions of a single variable. So, thus the equations x equals to x t, y equals to y t, and z equals to z t represents a curve in space, and the variable t is called a parameter, and for each value of t with a certain range. So, t has a certain range, let us say a less or equal to t less or equal to b, where a and b are both real numbers, corresponds for each value of t, there corresponds to a definite point p x y z of the curve, right. So, for example, if I want to write the let us say this is our curve in 2-dimensional space. Here they are talking about 3-dimensional space. I am just, for the sake of explanation, I am just taking this example. So, let us assume that our curve C is basically this circle. So, how do we write this curve in space using this formula? So, I can write x equals to x t. So, x t would be, let us say, cos t, and y equals to y t, and y t would be sin t, and I can choose t between 0 to 2 pi. All right. So, if I choose t equals to 0, then we have x equals to cos 0 is 0, cos 0 is 1 and sin 0 is 0. So, basically 1 0. Obviously, this 1 0 point lies on this circle. I can choose t equals to pi by 2, and then in that case cos pi by 2 is 0, sin pi by 2 is 1, then the point 0 and 1 lies on the circle, and so on. So, that means for every value of t, we get a unique point p. So, well, not unique, but there exists for every value of t, there corresponds a point p on the curve, because for t equals to 2 pi, we get the same point actually. So, for t equals to 2 pi and t equals to 0, we are getting the same point. So, for every value of t, there corresponds a definite point. So, we must have a point on that curve, and that point on the curve is obtained for that particular for a certain value of the parameter t. So, for every t, so t has a range, and for every t we will obtain a point on that given curve, and that curve is basically called as a curve in space. We can also have a sphere x square plus y square plus z square equals to 1, and then this equation would change. It would be cos t, sin t, and then cos t, so cos t, cos t, cos t, sin t, and then again so basically we have to use two different variables. So, then in that case it will be cos t and then some other variable, and so for a sphere it will be cos t sin t, and then we will have cos t, and then so you basically you got the idea how you formulate. So, x t, if it is a sphere, then we will have cos t sin t, and then y t would be cos t, and then z t would be just sin t. So, then in that case cos square t, yeah. So, that will be 1. So, again for a sphere you can give the formula in this fashion. So, yeah, that's one way to define a curve in space if the given curve is actually a sphere, and the parametric, this is also called as the parametric representation, is given by, if it is a sphere, then it will be given in this fashion. If it is a circle, then it is given in this fashion. All right. Now, and if we want to have this circle as a curve in space, let us say in 3D, then we write it as x equals to cos t, y equals to sin t, and we put z equals to 0. Now, we have a 3-dimensional representation. So, this is again a curve in space where z equals to 0. So, these are all tricks basically. So, we have a 2-dimensional circle, and if we want to represent it in a 3-dimensional sense, then basically the z component is 0. So, you just write z equals to 0 and x equals to cos t, y equals to sin t, and that is your curve in space whose z component is 0. So, that is how we write this curve in space. All right. Now, that we have a curve in space, we can actually be able to write, so let me put it in a nice sentence. So, in the language of vectors, a curve can be represented by an equation of type r equals to f t. So, basically the equation of the curve in space can be written as r equals to f t. So, let us take our circle case. So, for example, for that circle case I can write r is equals to f t, and f has 3 components. So, I can write f 1 t I, f 2 t j, and f 3 t k. So, f 1 t is cos t I, f 2 t is sin t j, and f 3 t is 0. So, basically we have cos t I plus sin t j. This is actually a function of t, and that is why we are writing f of t. So, f is a vector function of a scalar variable t. So, you see our circle can also be written as r is equals to f t. So, in the language of vectors, actually a curve can be represented by an equation r is equals to f t, all right, where r is equals to actually the vector o p. So, let me draw a figure. So, if I draw a figure, I can be able to write it as, so this is my x axis, this is my y axis, this is origin, this is z, and suppose this is our curve f, all right. So, this is my curve f, and suppose this is the point p x y z, this is my point q, x plus delta x, y plus delta y, and z plus delta z. So, I am going to make them merge, and this one is another vector. So, that is our vector o q o p, and then this is our vector p to q, all right. Now, this is r, and this is r plus delta r plus delta r, all right. Now, choosing 3 fixed directions. Now, I am just trying to put it in a nice word. So, choosing 3 fixed directions I, j, and k mutually perpendicular to one another, mutually perpendicular. That means I is perpendicular to j is perpendicular to k, and then k is perpendicular to I. So, they are mutually perpendicular to one another, and mutually perpendicular, we may be able to write, we may express the equation. Let us say this is our equation star, the equation star analytically as r equals to x. So, r is basically this vector, which is basically o p, and o p, p is my x y z. So, x I plus y j plus z k, but since x y z are all functions of t. So, this is nothing but x t I plus y t j plus z t k, right, and this is which is equivalent to the 3 scalar equations given by x equals to x t, y equals to y t, and z equals to z t, the equation from which we started originally. So, this is the scalar equation for a curve in space. Now, for every point on that curve in space, we are associating a vector. Let us say p is any arbitrary point on that curve. Then from origin we are associating a vector o p, and that is given as r. R is the position vector of a point p on that curve, and basically r can be, with the help of I, j and k, r can be written as x I plus y j plus z k, but x, y and z are all functions of t. So, we write x t I, y t j and z t k, and this is in a way, how to say, a way to write a curve in terms of vector, and that curve is actually a curve in space. So, just using this r is equals to f t, where f t has 3 components x t, y t and z t. We are, how to say, transforming that scalar representation. We are sort of finding an alternative way to write that scalar representation in a vector form. So, basically instead of writing x t, x equals to x t, y equals to y t and z equals to z t, we are just writing r is equals to, which is a function of t, x t I, y t j plus z t k, and that represents, that vector representation r t equals to that expression is same as the scalar equation. So, that scalar equation and that vector equation both are the same thing. It is just that it is an alternative way to write the same curve in space, and based on that, now we introduce several concepts. So, like if we had a scalar equation x equals to x t, y equals to y t and z equals to z t, since it is a curve in space, we can talk about tangent, we can talk about normal. Similarly, for this vector representation, the way we have did the vector representation, that is x t I, y t j and z t k, we can still be able to talk about tangent, normal and some other things as well. We will see what are those things. So, it is not completely different, it is the same thing, it is just that the way we are expressing it using the vectors is slightly different, but it is convenient. It is very convenient to write the equation of a curve in space in a vector form than writing it in a scalar form, and we will see what are its benefits over the time. And now, as I was saying that we can actually be able to define the tangent and the normal. So, we will start with the definition of the tangent. How do we define the tangent for the curve in space given by this vector form? All right. So, let us start. Tangent to a curve at a point P. So, we refer to the same figure, and when q tends to P. So, when q tends to P, then this will actually be how to say, along the direction of a tangent to this curve. All right. So, the formal definition would be the tangent line P t at a point P of a curve is the limiting position, of the secant P q joining P to a neighboring point Q when Q approaches P along the curve. So, this is we know already from our previous topics. So, when it is basically the tangent is nothing but a limiting position. So, that means when Q tends to P, this will actually be along the direction of tangent, or this is actually a tangent in a way, not along the, but it is exactly the tangent. So, when Q approaches P, then it will not how to say, go through this curve, it will actually be a tangent. So, it will actually be touching the curve, and that will happen when we are making Q going to P. So, it is basically a limiting approach, all right, or a limiting case. So, that means how do we define the tangent basically in terms of vector. So, we first show that So, how do we define the tangent? So, to define the tangent in terms of vector, we take 2 points P and Q, which we have already done. So, the points P and Q are basically x, y, z and x plus delta x, y plus delta y and z plus delta z. So, this one is for the vector r and this one is r plus delta r, all right. So, now then our vector r is OP, all right, and OP is FT. So, that is how we are giving the equation, and the point for the point Q, r plus delta r is the position of the point P at a time t plus delta t. So, at time t it is simply x y z, and at time t plus delta t it is now x plus delta x, y plus delta y, z plus delta z. So, that is the point Q, and in terms of the function f, I can be able to write t plus delta t. So, at the time t plus delta t, the point has moved along the curve to the point Q, and it is given as this way, all right. So, our curve, our line P to Q can be given by OQ minus OP, and this is nothing but FT plus delta t minus FT, all right, and we divide by delta t. So, then this will imply PQ by delta t is equals to f of t plus delta t minus FT by delta t, right. And now we take delta t goes to 0, limit delta t goes to 0. So, this is P to Q divided by delta t, and then this is again limit delta t goes to 0 and this whole expression. So, f of t plus delta t minus f t, both are vector, and then both divided by delta t, all right. So, we will have this thing here. Now, this quantity P to Q is nothing but that delta r, right. So, P to Q is nothing but delta r. So, I can write limit delta t going to 0, delta r by delta t is equals to f of t plus delta t minus f t divided by delta t, and then limit delta t goes to 0. So, this is nothing but our dr dt. So, when delta t goes to 0, delta r by delta t will go to dr dt. So, this is dr dt, and this is nothing but the derivative of the vector function f. So, this we already know from the differentiation. So, this is the derivative of the vector function f. So, that means that is dr dt or f dash t is parallel to the tangent P t, right, of the curve r is equals to f t at the point P where t is the parameter, and therefore capital R is equals to small r plus lambda times dr dt. So, capital R can be written as capital R minus small r is equals to lambda times dr dt, where so this equation represents the equation of the tangent line PT, where lambda is any arbitrary constant, r is the position vector, of P, and capital R is the position vector of any point on the tangent line. So, that means in this equation we have shown that dr dt is basically parallel to the tangent PT of the curve r is equals to ft. So, that means the position vector of any point on the tangent plane or on the tangent line capital is denoted by capital R, and this is basically small r plus lambda times del r dr dt. So, that means we can be able to write the equation of the tangent line as r minus capital R minus small r is equals to lambda times dr dt. So, this is basically saying that the tangent is parallel to dr dt, and this capital and small r are basically nothing but this is the position vector of the point P, and that is the position vector of any point on the tangent plane, and dr dt is basically the derivative of the vector function r with respect to t, and lambda is a constant. So, this is how we give the equation of a tangent line at a point P for the curve r is equals to ft. So, today we will stop at here. In the next class we will work out few examples that how we calculate the tangent line, although we saw in the previous chapter on level surfaces how we calculate the tangent line. So, perhaps we will do one more example, and then we will introduce the concepts of normal and binormal of a vector function, and then we will try to derive the Serret-Frenet formula. So, thank you for your attention, and I will look forward to your next class.